All right, so this is where we really get into calculus. So as we did with the tangent line problem, we took our distance between the 2 points that form the secant line, and we took the limit and we allowed the distance between those 2 points to approach 0. And as we did that, those 2 points got closer and closer and closer, and the secant line slope began to change more and more and more until finally those 2 points were right on top of each other. And at that point, the distance between the 2 points would have been 0. But we took the limit as that distance approached 0, and that allowed the secant line to essentially approach the tangent line. And so then the slope of the secant line approached the slope of the tangent line. So there's a very similar approach with finding the area under the curve. So Riemann hit upon something when he found that, okay, this midpoint works pretty well for a straight line, but if it's a curved line, it doesn't work so well. Well, you know what? The thing about curves is, and this has something to do with the tangent line problem, if you look at smaller and smaller intervals on a curve, they look like lines. As a matter of fact, you can consider a curved function to be an infinite number of points with tangent lines. And so what Riemann said was, you know what, why don't we let this width of the rectangle, we can call that delta x, or dx, the differential, why don't we shrink that? Why don't we take the limit and let the width of the rectangle approach 0? If we do that, then yes, the number of rectangles will approach infinity. But we will get smaller and smaller rectangles with smaller and smaller errors, and eventually the sum of all of the rectangles, the sum of the infinite number of rectangles, should converge to the actual value of the area under the curve. And that was the breakthrough and the connection to calculus. So here is delta x. Here's the width of the rectangle. So delta x is b minus a divided by n. So what are these letters? Well, AB is the closed interval that we're taking the sum over. So b is the right-hand boundary, a is the left-hand boundary, and we're just finding the difference between those two. And now we want to subdivide them by the number of rectangles that we're going to use, and that's actually what n is. So b minus a divided by n gives us the width of the rectangle delta x. Now remember what we said we were doing. We were taking the delta x and multiplying by the height. And the height is actually going to be found by using the function and taking the function of some corresponding c value on the x-axis. So you can see that what we have here, just this part, f of ck, where k is an index for a given rectangle. How many total rectangles do we have? Well, we have n. And so this is sigma, which means take the sum. So we're going to take the sum from k equals 1 to n of all of our rectangles. We're going to plug in the corresponding value from the x-axis, c sub k, which corresponds to the given rectangle. Plug that into f to get the corresponding height multiplied by the width, which is delta x. Add them all up, and then we're going to let the number of these approach infinity. In other words, add up the infinite number of rectangles with area f of ck times delta x, length times width. That's the area under the curve bounded on either side on the closed interval by those values a and b and the x-axis. This is equal to the integral from a to b of f of x dx. So here are the steps for using Riemann sums. 1. Draw a rough graph of the function over the interval. Use this formula for delta x, so you'll be given an interval AB, and maybe they'll tell us how many rectangles to use. So we can find delta x. Then we compute coordinates of rectangles at either the left end or right end. And then we compute the areas of each rectangle based on our left hand or right hand Riemann sums. Finally, add them up. So this is an approach that will work for left hand and right hand Riemann sums. We'll talk a little bit more about midpoint Riemann sums in a moment.